Okay, good afternoon. I'm Peter Michelson, chair of the physics department here at Stanford. And today is a special day for me because I don't normally introduce the speakers at COLLOQUIUM, but today I have the privilege of introducing a colleague, Andrei Linde, who will talk to us today about an engineering project. We're very close to the School of Engineering here. Andrei is going to talk about the biggest engineering project literally of all time. And I think we'll learn a lot. But before I turn this over to Andrei, I just want to say a few words about Andrei. I actually read his biography again and realized that I've known him for almost 30 years. So Andrei's been here since 1990. And I think when he first came to Stanford, that was in the very early days of some of the theory that he'll allude to today, inflationary cosmology, and it's come a long ways in 30 years, and we still don't know all the answers. It's one of the things I think we'll find out. But Andrei, for his work in inflationary cosmology principally, has received a number of recognitions, and I won't read all of them, it's a long list, but I mention a few. He's a member of the National Academy of Sciences and also the American Academy of Arts and Sciences, and he's received the Oscar Klein Medal, the Dirac Medal, the Gruber Cosmology Prize. He was a recipient of one of the first fundamental physics prizes, and more recently, the Kavli Prize in Astrophysics. And I think today you'll hear about his work that led to that recognition. And I think he's going to give us a very broad perspective about reverse engineering the universe. And I've got to draw attention to the first slide. Maybe he'll explain the cover slide. It has something to do with another talent that Andrei has as a photographer. So, Andrei.
Okay, thanks a lot. I'm happy to talk here. And that's actually an engineering project in Italy. There's a town of Orvieto, which is on the top of a big stone. And they drilled the well in it so that if enemy will attack, they will be able to take water from it. So if you go down the well, which takes some time to do, then water drips on you, etc., and it's very, very scary. But then when you photograph upstairs, there is something. Well, depending on your tastes, you may think about it like what it is, a black hole or a Big Bang or whatever. So we are going to talk about related issues. We are going to talk about Big Bang. And here is our idea. Suppose that of course, nobody is obliged to take this attitude. It just, I decided to look at the way how we study cosmology from a slightly different perspective. So what if I would try really to make a universe? Would it be really difficult? Would it be okay? Can you do it easily? Or it's very, very complicated? And can you do it like in a foolproof? Which means that, for example, if your radio doesn't work, then you stamp on it and it starts working. So something like that, that it's pretty stable with respect to different changes. And before discussing the different possibilities, the first thing to do is just to look at what we know right now. Because right now we know that galaxies fly away from us, and then we may just look at them and play the movie back in time and see how it all started, hopefully. So just some pieces of data. Oops, no. Okay, just a second. I need to relearn how to use this. Okay, so the distance from Earth to the edge of the observable part of the universe is approximately 46 billion light years. And you may wonder, how is that it is 46 when you know that the universe existed perhaps about 14 billion years. So it is 14 billion years, right? But the universe at that time was expanding. So it is bigger than you may well think. It is bigger than just CT. The total mass of the observable part of the universe is approximately 10 to the degree 50 tons. And that is now. And one would expect, okay, so this is what you need. You need 10 to the 50 tons to start everything. However, when the universe was young, it was filled with radiation. And when it was smaller, the wavelengths of photons there was shorter and shorter and shorter when you move to the beginning of times. So when we recalculate, shorter means larger energy. So in the beginning, the universe was much more fat than that. Its total weight was about 10 to the 80 tons. So that is pretty heavy, and that's the question, how can you even, well, start thinking about creating this? And one way of approaching it is first to describe this in some terms which have less of these meaningless numbers, like kilometers and kilograms and tons, whatever, something invariant. And in well, general theory of relativity in quantum gravity cosmology, there is a convenient system of units. C is equal to 1. So when somebody asks whether the speed of light can be different in the early universe, the answer is C is equal to 1. I measure speed of light in units of speed of light. H bar is equal to 1 and gravitational coupling constant is equal to 1. Well, about this, different people use different units. Sometimes they say that G is equal to 1, sometimes it is, well, with the accuracy of a factor, a square root of 8 pi or something like that. But never mind, it's about 1. Okay, and if you use this system of units, description of the universe becomes somewhat simpler. So in this simple language, the density of the early universe, if you trust the Big Bang story, the density of the universe behaved like that. Density was proportional to 1 divided by time squared in these units, okay? So when time was equal to 1, density was equal to 1 in Planck units. These are Planck units, okay? And at the moment when t was equal to 1, density was so large that quantum fluctuations were so large that there is no yet reliable description of what happened there. Possibly it can be constructed using string theory. It's a very, very challenging task. So we will start description of the universe starting from time equal to 1 or greater, okay? Because we just has nothing to say so far about what happened before. Okay, so in normal units, time equal to 1 corresponds to 10 to the minus 43 seconds. Planck density corresponds to approximately 10 to 94 gram per cubic centimeter. Again, this depends, or slightly depends on how exactly you define what is the Planck density. Planck length, it is c multiplied by t. So if you take this time multiplied by speed of light, which is 10 to the 10, 3, 10 to the 10, whatever, it becomes 10 to the minus 33 centimeters. So this is Planck length, okay? And if you do normal thermodynamics, study hot Big Bang universe at the time when it was, well, just created, and look at this density and calculate how many particles it contained in unit of length, which was Planckian length. And the answer was that one single Planckian domain contained about 1 particle per this Planckian domain. So everything is maximally simple. 1 particle per 1 Planckian domain at the Planckian time, and the domain has Planckian length. So that is, and if we try to go down, back to smaller values of time t, we just cannot say anything. Classical space-time in general, space-time fluctuated so strongly that classical space-time did not have any easy meaning at that time. But we will discuss it maybe in this talk, okay, later. So let's go forward. So what is difficult, what's so difficult about creating and controlling this universe? Okay, so if we believe into standard Big Bang picture, then it's just like with this movie. You have all of these galaxies, all of these particles, and back in time, you have the same particles, the same galaxies, they just denser and denser and denser, and you have the same number of photons. And the general law is that from the moment of the Big Bang and to the present moment, the total number of particles did not change much. It changed a little, because some of them were unstable, some of them reacted with each other. They can a little bit of eat each other, but mostly they were decaying, and so it may be slightly less particle to start with than the total number of particles right now, but it was of the same order. So the total universe consisted approximately of 10 to the 90 degree particles at the Planckian time already. But at the Planckian time, one Planckian length contained one particle. So then, at the Planckian time, you needed to have 10 to the degree 90 Planckian lengths. So our universe must be 10 to the 30 in this direction, 10 to the 30 in this direction, 10 to the 30 in this direction, much greater than Planckian size. And its size, therefore, was 30 orders of magnitude larger than the causality distance. Speed of light multiplied by time was 1, but we needed to cover 10 to the 30. So if somebody is so powerful that he can create the universe, but he actually can control only 10 to the minus 90 of the whole universe, that is the main challenge. So if you believe in just think about it. We think about somebody have created the world. Okay, how you create the world? Oh, I created. Here it is. Bam. No, I can control 10 to the minus 90 of the whole universe. So nobody can be powerful enough to do it. Okay, so that's the problem. And the question is, can we do any better than that? And that's the challenge. So it looks like we need a miracle, right? Okay, because that is possible. Okay, so we can't have a miracle, but okay, so let's try to do it. Here is a basic idea. Suppose that our universe is filled with energetic vacuum. And that's okay. It's just like cosmological constant. That's dark energy, for example, right now. It is energetic vacuum, okay? So you have vacuum which contains some energy. Depending on what energy of this energy of vacuum was in the very early universe, this number can be actually quite large, okay? So this is slightly simplified Einstein equation. Actually, it's quite okay if it is for the flat universe. So Hubble constant squared is proportional to the speed of this expansion of the universe divided by its side squared, and it is proportional to the energy density of the universe. Energy density in vacuum state. So now you look at this equation and you solve it. This is the simplest equation of mathematical physics. And it shows you its solution. It shows that the universe was exponentially expanding. Universe was exponentially expanding. Vacuum, energy vacuum remains vacuum. It's just nothing. Its energy density remains constant and it grows exponentially. So the total energy inside grows like volume because density is here is constant and it grows of the size like that. So volume grows like that. And therefore energy, total energy stored in the universe was growing exponentially, and if so, if this vacuum state later can decay, it can produce exponentially many particles. You can start with a Planckian-sized universe, no particles inside, just a little bit of heavy vacuum there, bam, and very shortly you have lots and lots of energy because energy was exponentially growing, like chain reaction producing the universe. And that was one of the basic ideas of inflationary theory, and that was well proposed here at SLAC. So that is, however, another Alan who was fighting with inflation. Okay? He said that if I made myself too clear, you must have misunderstood me. So the idea was so simple, so transparent, and that is dangerous sometimes. So if something looks too good to be true, sometimes it is really the case. And this is the reason. If the universe is really empty, if it's really in vacuum state, how can we even tell that it is expanding? That's just the simple question you ask yourself. Okay, so we are told that this is a vacuum state, but this is cheating, because in vacuum state there is no markers which will tell you that the universe is expanding. And this is not a formal problem. The universe with a constant positive vacuum energy is de Sitter space. And in de Sitter space, you can introduce several different coordinate systems. In one of these coordinate systems, de Sitter space first collapses and then stops collapsing, starts expanding. In another set, it's only expanding. And yet another set, it is actually static. And it is not a joke. I remember how I was, well, when this scenario was introduced, and I came to one of my advisors at Levity Physical Institute, and I explained him the theory, and he told me, but no, that's impossible, because de Sitter space is static. Okay, so that was the idea. So something was slightly wrong, but it's actually very, very physical. Because if you do not have any preferable coordinate system in the vacuum, then you do not have any preferable choice of hypersurface of a given time. And therefore, you do not know when this vacuum should start decaying. So it decays chaotically, and as a result, the universe becomes very inhomogeneous. And it is really, really a problem. So Alan Guth with his collaborator Eric Weinberg, not Steven Weinberg, about a year and a half after he gave his idea, published a 100 pages paper proving that it's impossible to improve his theory. Stephen Hawking came to Moscow proving that it's impossible to improve his theory. And we have had a very interesting encounter with him when he was, well, discussing it at the seminar in Moscow, and I translate him, but that is not for his talk. Okay? So, and moreover, in the original scenario suggested by Alan Guth, the problem was actually not very much solved, because the process which he proposed was supposed to start at the time which was already 100,000 times greater than Planckian time. So the universe at that time was already huge. It contained already many causally disconnected parts. And yeah, this was not a real problem. It is still the universe which was not controllable. Okay? So it required some, well, mostly psychological, it was mostly a psychological problem, I think, because everything in the theory is basically, at least basis of the theory is relatively straightforward, but it was very difficult to get rid of what Big Bang theory suggested us, to discard the possibility that the universe required hot beginning, that it was large from the very beginning, etc. And then we eventually came with something which in the simplest form can be described by this potential. So first of all, instead of energetic vacuum, we start studying scalar field like Higgs field, which is very popular now, okay? So scalar field, and the scalar field may have very simple potential as a function of the value of the scalar field. And the condition was that if we find such a situation where the scalar field stays here, not rolling fast, then its energy practically does not change when the universe expands, and then the universe was inflating. Okay, so this was the basic idea. It was not so easy to realize it, so it was necessary to write down all equations, and this is equation which I already shown you. Here, instead of energy of vacuum, you have potential energy of the scalar field. This is equation for the scalar field, and this equation is very similar to equation for harmonic oscillator. And there is the term which appears because of the expansion of the universe. The faster the universe expands, the larger is this term, which plays the role of the friction term. And if this term is large, scalar field really stuck. It stucks to the wall, it does not slide down, okay? So it's like, you know, you have harmonic oscillator normal, harmonic oscillator anharmonic decreasing, and you have overdamped oscillator. So if Hubble constant is very large, then the oscillator is overdamped for a long time, scalar field phi does not change. This is like a constant, and then we reduce the problem which we already studied. Universe expands almost exponentially, and this almost is crucially important. If this potential is very flat, like constant, scenario doesn't work, just like Alan Guth scenario. If it is very steep, scenario does not work because friction is insufficient, the field falls down fast. And you need to be somewhere in between these two, okay? So that was the trick. And that is the basic realization. So you start with a Planckian size domain, and if this in Planckian size domain, you have potential energy density larger than gradient energy density and kinetic energy density, then the universe starts exponentially expanding, but gradient density falls down because the universe rapidly expands and all gradients become exponentially small. Kinetic energy falls down because of the friction term. Only potential energy remains, and that is like vacuum-like expansion, where potential energy is very large and changes slowly. So you may start with Planckian size domain, and during this amount of time, the universe becomes that big. Okay, and that is in any units of its mile and centimeters really does not matter. What matters is that if it was very squashed, like it was, for example, not a sphere but a cucumber, it expands, you live on the surface of the cucumber and you see it flat. So you understand why our universe has geometry very close to, well, geometry of a flat space. Why, if Cleat was right, why it is so uniform? Because all non-uniformities were stretched away. So that is really, well, cool if it works. However, one may ask, but we understand that you must cheat us somewhere. Well, how about this energy conservation? Because you say that you start with a Planckian size domain, and a Planckian size domain has less than 1 milligram of matter. And right now you have these 10 to the 50 tons of matter. So who gave you these 10 to the 50 tons? And that is interesting mathematics. Energy of matter in the universe is not conserved, okay? It's not what we learned in school. In school does not expand. The universe does, okay? So when you have a hot universe filled with photons, when the universe becomes 2 times greater, the wavelength of a photon falls 2 times. So energy becomes smaller. So in a normal hot Big Bang universe, energy of the universe decreases and nobody objected against it, okay? And that is the way how you can understand it. That's just the way how, well, energy changes when the volume expands, this normal thermodynamic relation. And usually pressure is positive, but not for the vacuum. For the vacuum-like state, for the state of the scalar field which changes slowly, pressure is negative. And therefore, for the slowly rolling scalar field, total energy starts growing. Okay? So there is no, I would not even look for a cheating here because I've solved these equations, I know how to solve them. Okay? But nevertheless, it looks like it cannot be. And then there is another way of explaining it, and this another looks very esoteric, but in some sense it's very important. When you calculate the total energy of the universe, which includes energy of all particles, plus also something which you should associate with metric of space, with gravitational interaction of planets, the total energy can be proven to be exactly 0. That is a strange thing. You have energy of matter and energy of gravity. And if you have a regime where energy of matter can become exponentially large and simultaneously energy of space becomes negative but also exponentially large, then the total remains 0, but we do not care about this. This is what we carry, this energy of particles. So it's kind of magic trick, but this magic trick is no nonsense. It's not really a cheating. So if I will cheat you, sometimes I will tell you. Maybe. Okay, so if such instability is possible, it appears over and over again. It's like, you know, if something can go wrong, it goes wrong. And the universe grows, and in one place it can go wrong, then it can continue going wrong. And this continue going wrong means that it can start exponentially expanding in new places. So this is what is called eternal inflation. When the universe starts inflating, sometimes it have a chance to have this eternal inflation continuing in different parts of space. Origin of structure. Well, that is a dangerous one. And I would never start doing it if I did not have a friend in the corridor of Liberty Physical Institute, Slava Mukhanov, who studied quantum fluctuations in the situations like that. And I asked him, how can we produce a structure? Because the universe is exponentially expanding, and all inhomogeneities, they just become exponentially small, okay? And he told me, yeah, I know how, because quantum fluctuations produced during inflation, they are stretched away and they actually accumulate on the top of the previously generated fluctuation or previously generated, and as a result we get fluctuations which later are responsible for creation of galaxies. So we have a fantastic regime where galaxies are produced by quantum fluctuations. And when he told it to me, I told him, you're insane. Galaxies are classical. Quantum fluctuations are quantum. And it took me a little bit to understand it. And then I say, oh, that is something. And that became one of these main features of inflationary cosmology. So we start right now, this is a theory, okay, but there is a way of checking it. So Planck satellite, $1 billion for checking this strange stuff, okay? $1 billion, well, it stopped already getting data, but the data which it received, so many that it is still trying to make sense to all of them, and they have already several data releases, and they are promising the new data release. The last promise was we will publish it in the 1st of April. And no, well, good thing that they didn't. Okay, so now they're saying maybe in June. Well, so this is what they produced. They produced something which looks like I could do much better just going to Home Depot and buying a spray for $5. So what it is this? Why it is so exciting? These are small fluctuations of the temperature. They look at the sky and see that not all parts of the universe have the same temperature. They measure effectively temperature with accuracy 10 to the minus 5 of a Kelvin, something like that. It's just totally insane. Somebody would tell me that it is possible. And they travel all around the United States. They show this picture and nobody excited for whatever reason. Because it's hard to explain that what we see right now is the tiny part of space during inflation, which was exploded by inflation, which produced quantum fluctuations, which were stretched, and they are right now positioned on the largest photographic plate ever, the whole part of the universe which we see right now. We observe them, we see, first of all, it is time machine, which brings it back to the time about 10 to the minus 35 seconds after the Big Bang. No other experiment, okay, 10 to the minus 35 seconds after the Big Bang. And there are fluctuations which are produced at that time when there was nothing but this expanding vacuum state, okay? And then they measure the spectrum of these perturbations on different sizes, on different angles. And this red line is a prediction of some of the simplest inflationary models, okay? So each spot is what they would consider separate experiments because it is a different, multiple momenta for that. And here, many such experiments. Here, situation becomes a little bit less certain because we do not have many pieces of the universe. This small l means that I look at the universe like that. So half of the universe here and half of the universe here, there is no reliable statistics. But if you have small angles, statistic is reliable and that's how it behaves. So it just, well, fantastic. And there are several different predictions of inflationary universe which it did, which have been tested, and the fight about them was quite spectacular. Like, for example, in the 90s, in the middle of 90s, everybody believed that omega, which is the ratio of energy density of the universe to the critical density, if it is 1, then it's flat universe. That's what inflation predicts. Okay? So at that time, everybody said that it's 0.3. And therefore, everybody was scared that inflation cannot work because it's 0.3. We were trying to invent models of inflation which would predict 0.3. And I myself invent several of them. And they were so ugly. And all of them died. The only one of these models which I know survived was the ugliest of all, and I can tell you about it. It was full responsibility because I invented it being drunk, and it was in Spain waiting for flamenco show. I came there and I had 3 hours, and I had only a metro ticket to invent it. So they let me give me a table and asked him, can you give me a paper? And they did not know what kind of paper did I need, but eventually they just gave me a bottle of wine and I was standing there. So this model survived, but this is manifestly ugly. And in 98, it was found that remaining 0.7 is the energy of vacuum. It is this dark energy. And when it was discovered, it was like, oh, it was 0.3, and now, due to Planck efforts, it is 1 plus minus this 0.5% or so. I would not bet about 0.5% or percent or what it is because, well, it's experiment, and every one of us, we are all just looking, how do they do it? It's just magic, but this is what they say to us, okay? And there are several different predictions. I wouldn't like to discuss right now lots of them. I would pay attention to one thing. So first of all, this search for experimental data still continue on many, many fronts. Here at Stanford University at Kaipak, many people devote their life to do something closely related to testing these things. Planck data should be appearing shortly, and this was especially a spectacular part about the bicep Keck experiments, which was maybe misinterpreted when it was first released, but it still remains the absolute record-breaking experiment trying to find gravitational waves produced in the early universe. And since that time, for 4 years after it was released, they're still in championship position as compared to study and trying to find out this. So if we find gravitational waves, then we learn quite a lot about the universe. It will be just pure magic. It would be fantastic. If we do not find them, it's also possible because not every inflationary model produces gravitational waves of large amplitude. All of them produce these perturbations for galaxies. Okay, they're called scalar perturbations. For gravitational waves, it all depends on the model. In some models, they can be very, very small. Now, looking at the Planck data, not all theories feed the data good. So these are Planckian data, this Planck 215. One should understand that these data are still preliminary, that these data move slightly from one side to another, depending what kind of stuff they included there and what kind of they do. So it's very premature to make any suggestions, but one probably is right. The simple model which I proposed a long time ago in '83, unfortunately, it is ruled out. It is, so you may, okay, let me go back slightly. Okay, so you may even ask, why did I tell you about that? You will see shortly. Okay, so this model is out. Okay, here are some models which were introduced by Ivo Silverstein and her collaborators. They're based on string theory, and if it will be supported by experimental data, that will be fantastic, because it will be double success both on string theory side and on the side of cosmology. This is natural inflation here, kind of moving outside of this area, but again, it's, well, we are waiting for the continuation of this. These two lines, depending on some, well, assumptions of where in the early universe it all started, these two lines correspond to the alpha attractors models. And alpha attractors were invented in our papers with Renata Kalish, who is here. I must say that I do not put there lots of, well, names in all of these slides. It is not what everything, okay. 90% of the papers during the last 5 years we have been writing together with Renata, and they were about these alpha attractors. So what are these alpha attractors? This is just formal representation of my first simplest model, m squared phi squared. Okay, this kinetic term, a gradient term. This is Einstein action, and that is potential of the scalar field. And the only thing which you need to do to go to alpha attractors is to modify this kinetic term. And this modification looks scary, because at some moment this part in the denominator make kinetic energy singular. Okay, so you may think this is something very, very dangerous, but the situation is opposite, because you can make a transformation from this field to canonically normalized field. So if you just solve equation d phi divided by this is equal to d curly phi, you solve this equation, you get normal kinetic term for this field, but the potential becomes potential of a hyperbolic tangent. And hyperbolic tangent behaves like that. Okay? So my parabola behaved like that, and hyperbolic tangent goes to a constant. And the potential start looking in the following way. Suppose I have this model for this special field, and I have normal model, normal field, and there is a potential as a function of both of them. Okay? And now I take into account that one of them is this special, having this kinetic term of special type, and go to canonically normalized field, and the answer will be like that. Potential suddenly start looking like these hyperbolic tangents at infinity. So you start, let me go back, you start in the theory, which is so bizarre and such a sharp mountains that you would never guess that inflation is possible there, because inflation requires flat, requires flat potential inflation. Okay? And here you have them. That is what I mean foolproof. You start with garbage, but somehow it self-organizes in the way to achieve more or less automatically, just because of the existence of the singularity. This does not mean that the theory is right. I must say from the very beginning, this does not mean that the theory is right. Theory looks beautiful. Theory may be wrong. These things are quite compatible with each other, unfortunately. Okay? But this theory looks foolproof. So if you have some examples of a foolproof theory, you have a hope that in the end, when we work a lot, what will eventually occur, either it will be something which does not require to be foolproof, just by chance we have what we have, or maybe something will be really stable. Okay, so let's go forward slightly. So what alpha attractors, what it does, it stretches the potential, it makes them flat. Okay, then after that, inflation becomes possible, and inflation makes the universe flat. So there are two mechanisms bind together, and they all responsible for one thing, how to make the universe big and flat. And then I found that Renata is, well, sitting near a computer and searching something about Escher, and I asked her, why are you spending your time on Escher? Let's work. Okay, and then, no, let me do it. And she continues, And then what emerged is that Actually, this geometry with this singularity there is well known, and that is something which is called Poincaré disk. And here, normal situation at small values of the radius, normal situation. When you go further and further, these angels and demons become smaller and smaller, and there are infinitely many of them. And if you start going there, it will take you infinitely long to go there to infinity. You just packed infinity into this sphere. And then what we did effectively, this was my quadratic potential, okay? And it was going upstairs. But if you project onto it this Escher disk, then most of the angels, they live here. And then if you go to proper coordinates, that's what you see. You have here quadratic, but at large distance it flattens. And then because of this flattening, you have this agreement with experimental data so far. Who knows what will happen later. This summer we learned that if we bend this potential in angular direction, it really does not matter because the field does not want to go down in this angular direction. And we looked at how is that? The field must go down. Yeah, but if you look at the distance in the angular direction, this distance in this special geometry is exponentially large. So it takes lots and lots and lots of time for the field to move in this direction, and quite quickly it goes in that direction. So all motion of the field in this two-dimensional universe becomes effectively one-dimensional. Not because this is a potential which does it. Potential becomes almost irrelevant here, but because geometry forces the field to move only in that way. So you have, again, this foolproof thing. You make an error, you make mountains, and nevertheless, all of the theories, depending on the parameter alpha, this is for extremely large alpha, this is for alpha of the order of 1, which is more natural, and I give you that. And then these are alpha attractors, and then we ask, how then can we have inflation with alpha attractors? Because I started, we needed inflation to start at the Planckian density. And here the height of the potential in alpha attractors, in those of these models which describe experimental data, this is 10 orders of magnitude below Planckian. And we look at it and say, oh my God, it does not work. And then we start thinking again, and the answer to this question is actually pretty simple, okay? Well, technically, it's extremely complex, and that is Senatori, who is sitting here east, was working here at Kite Park. He was simulating the process and finding what happens in the early universe in this scenario. But you can have a general idea as follows. You have this potential, which is produced here, and it's practically cosmological constant everywhere except for this narrow region. And so it's almost cosmological, it just here it is different from cosmological constant. And then think about the universe. Oops. What? Yes. And think about the universe which contains this cosmological constant. This is what we have right now. We have right now dark energy, okay? And there are some places where you have galaxies, and there are some places where you have black holes, so who cares? They are running away. And 100 billion years from now, there will be no other galaxies around us, despite the fact that they are heavy, they are much more dense than the, well, energy density of the universe on average, but the universe does not care, it continues expanding. So they are flying away. And therefore, what looks is the following. Start at the Planckian density in a small compact universe. And if the universe does not, well, rapidly collapse, but continue expanding, then all density sitting in all normal matter is diluted by expansion, like 1 divided by t squared, but the energy density of vacuum doesn't. So then eventually all of these inhomogeneities disappear, and we end up with expanding universe. It looks very simple. It's actually not that simple, because if the universe is closed, then it can collapse instantly in the Planckian time. But if the universe is open and compact, or flat and compact, then there is no reason for it to collapsing. So there is some strange conclusion in this model. It's easier to start with the universe which have a shape of a bagel rather than the universe which have a shape of a sphere, which maybe explains why before each colloquium at Stanford they serve you these bagels. Okay. Symbol of the universe. And now the simple intuitive interpretation of why inflation is possible in this model. You know that this person, okay? So he was saying that if it is necessary, then we'll be dropping money from the helicopter. And this was scary because everybody expected this might lead to inflation, except for if all money dropped to water, then of course nothing happens. Okay? So what happens here is that you have potential, which is like a flat plateau, and the helicopter sends the money everywhere, and only if they land here, there will be no inflation. But if they land here, it's just like a cosmological constant. So inflation is nearly, well, inevitable in this scenario. So as simple as that. Again, this is foolproof. You just drop it somewhere, okay? And most cases will be successful. What I did say about this, Alan Greenspan, who say just don't trust. Okay, yeah. Well, yeah. Now, these are predictions of these alpha attractors which can be studied in the future experiments involving gravitational modes and everything. This gray line, this is what they predict. This part is what was illustrating presently existing results by Planck. So we are close to what is reasonable. Again, this does not mean that the theory is right. We're just trying to do something, and let's see what next generation of experiments tell you. Can we see the moment of creation? Because right now we have a successful theory, we have lots of experiments, let's play the movie back. And the answer is that in the old Big Bang theory, when we can play the movie back, when we look just at the sky, okay? So the whole idea was that when we're looking at the sky, when we look further away, we see the older and older objects, okay? And when we look maximally further away, we see the Big Bang. So we cannot really see it using just photons, because closer to the Big Bang, everything is not transparent. It's just like our sun is not transparent to light, but it is transparent to neutrino. Okay? So early universe was a little bit more transparent to neutrino than to photons, but it was absolutely transparent to gravitational waves and to gravitons. So if we are so smart as to, well, catch gravitational waves from the Big Bang, we will see the Big Bang. And that was the old story. And that is not the case in inflationary theory. In inflationary theory, what we study, fluctuations produced during the last stages of inflation. At that time, these fluctuations were produced when the energy density of the universe was approximately 9 or 10 orders of magnitude below Planckian energy. 9 or 10 orders of magnitude. And these are reliable data. Based on the present bicep Keck data, one can find out that this amplitude of tensor fluctuations per scale or whatever from the experimental data, we know that what we see right now was produced at energy smaller than 10 to the minus 9 approximately. Okay? If we want to study effects produced at energy higher than that, we must go exponentially far away from us. In principle, it is possible. In practice, no way. Because we have in our universe background of exponential expansion, cosmological constant. And it takes stuff away from us very, very fast. And we can see only at a distance approximately this 14 billion or whatever billion light years away from us, and we cannot look any further. So we cannot see anything which happened when the universe was at the density larger than 10 to the minus 9. And certainly we cannot see anything that happened after the Big Bang. So this was a very surprising answer to me as well, kind of limiting what we wanted to do. We used cosmology to find out what happens at the moment of creation of the universe. And the answer, we cannot do it, okay? So that is too bad. In this theory, we cannot. And then look at it, oh my God, that is so good. Because what does it mean? This means that whatever happens there, and we so far do not have theoretical tools to fully understand whatever happened there at the Planckian density. Whatever happens there is none of our immediate concern. It's important, but it is not something that is going to affect much what we see right now in the sky, because the singularity is over the horizon. It's the same situation as a black hole. Inside the black hole there is a singularity. Oh, but here is this Hawking radiation, here is a property of black holes, so we can know quite a lot of stuff about black holes without knowing exactly the detailed theory of the singularity. So good thing about inflation, and again, foolproof. We may not know much, and it still nevertheless may describe what we see right now. But there is something else to it, and that something else I wanted to tell you even more about it, because I've never seen this pronounced clearly. By observing our part of the universe and playing the movie back, what I would expect to see, play the movie back, right now this 10 to the 90 particles. So I would expect to see all of these particles coming closer and closer and closer and closer, not, well, losing their identity. And this is not the case in inflationary universe, because in inflationary universe everything was produced in the Planckian side domain, which contained 0 particles in it. So how about that? I'm playing this, and then these galaxies just embrace each other and totally merge and then dissolve in the vacuum. Does not make any sense. And it does not make any sense for a good reason. But in order to understand it, we need to return to quantum mechanics, because all of this is quantum mechanics. Without it, all of this would be unexplainable. So this Schrödinger cat paradox, which is known for 100 years. For 100 years, people write papers explaining differently and hating each other guts for wrong explanation of that. And Copenhagen interpretation, many world interpretation, many mind interpretation, consistent histories interpretation of quantum mechanics, many of them. And that is Schrödinger cat, and it may be alive and it may be dead. When we play the movie back, there is some miracle here, a quantum process, but in the end, it is just Schrödinger cat. It was invisible, slight, well, transition here, some quantum arrived, but there was Schrödinger cat here. But in the early universe, there was no cat. This is what was there. This was vacuum, there was vacuum, and it was expanding. Universe is expanding, but there was no cat. And then suddenly, you have dead cat and the live cat, and we play the movie back, and there's no cat. And if you have anything from this talk, this piece of movie, I've never seen it anywhere. So I just took this and then I whitened it, some part from the... It's totally insane, you know. You have no Schrödinger cat to start with. Okay, so this is much more complicated than any other interpretation. You start because it's quantum field theory. In quantum field theory, describing the process, in quantum field theory, the total number of particles is not conserved. You can have 2 particles produce 10. You may have 10 particles, you produce 10 to the 90. But the interpretation of that is much more complicated. There was no cat. Okay, so it's really quantum mechanical. Now we're going to something else, and I have 5 minutes to conclude. Well, yeah, okay, I will do what I can. So this is what Einstein wanted from the fundamental theory describing everything. And he have written it in his autobiographical notes, which is shortly before he died. He just written, "This is my wisdom, this is what I wanted to achieve." And he said, "I would like to state a theorem which at present cannot be based upon anything more than a faith in simplicity. That was just magic, like this wise men say that the theorem based only on phase, okay? So this is that all nature is unique. All of this coupling constant and masses, etc., they could not be different because everything else would be logically inconsistent. And we were trying to prove, we were trying to explain why it is so. You start with a red universe, and it blows up and becomes red everywhere. So we kind of solved, well, fulfilled his dreams, we explained everything. But then we were up to a surprise, because we may start not with a red ball, but with, show me something, with a football, like that, okay? So this part is red, this part is blue, and then you wait, and it becomes exponentially large. This part is blue, and it has the size 10 to the degree 1 million, okay? And everybody living here will try to prove, like Einstein did, that only blue universe is possible. And somebody living here will trying to prove that only red universe is possible. And we have here something which is called multiverse. And some people are sincerely hate this idea. I cannot understand why. This is like you have on Earth. You have US, you have China, you have Russia, you have whatever. So that just happens, okay? And you have different people around, and they have all t-shirts of different color. It just happens. Why hate? Okay, so so pessimist would say, if each part of the multiverse is huge, we will never see other parts, so it's impossible to prove that we live in a multiverse. Optimist will say, if each part of the universe is huge, we will never see other parts, so it's impossible to disprove. Okay. What Einstein said, I would rather be an optimist and a fool than a pessimist and right. Yes, okay. And this scenario is more general than the scenario of the universe. It just, well, think about it. Like a person thinks that water can be only liquid, because it's water and it can be only liquid. And then they take a ship, and well, for all of his careers, he encountered no icebergs. And then one night he encounters it, okay? So he can hate it, whatever he wants, but the Titanic goes down. So, so that is what happens also if we even start with the universe, then because of quantum fluctuations it become multicolored. This is an example of some model, never mind what it is, supersymmetric SU5 model. It has many different minima for the scalar field, and these quantum fluctuations may bring this field from one minima to another. And then the universe becomes exponentially large, expands, and what we have is something which I called Kandinsky Universe. It looks like that. You start, for historical reason, with a red universe, and then it starts changing, and the colors change. It continues exponentially expanding, and gradually becomes divided into different parts with different colors. Some corresponding to SU5 minimum, some corresponding to SU4, some corresponding to something else. And these parts are exponentially large. And in the end, it continue growing, and start then solidifying. Some parts of it acquire some color which does not change anymore. So this is exponentially large part of green, exponentially large part of red, exponentially large part of blue. I stop this right now, okay? And oops, no. Okay, I'm just going here. No, here. Okay. So what happens at the end? You have the universe consisting of different, exponentially different parts, even if you start with one color. So how can you forbid this? And then it offers you some advantages as well. And then we learned that in string theory, there are many different vacuum states which allow you, the universe, to exist with different properties. And this was the number which existed, well, popular at the time, 2003. And then if you ask Eva Silverstein, she would tell you, no, it's not 10 to the 500. It's actually infinite number of different colors. So then, yes, you can paint it whatever way, and you choose your own universe. And then in different parts of the universe, cosmological constant can be different. And then you live only in the parts of the universe where you can live, because if the cosmological constant is too large or negative, you cannot live. You can live only here. And then you have a plausible, not conclusive, but plausible explanation of why vacuum energy at the present is so small, so extremely small. And so far, after these proposals have been made, nothing better emerged. So we do not think that this is, well, totally clear explanation, but we think that if somebody can come with something better, then let them do it. This was, I'm coming close already to the end. This was, well, this year, Renata and I were in Leiden University, and she got this Lawrence professorship there. We gave some lectures there. And at every corner there are some portraits of people there. Einstein was working here, De Sitter worked here, Lawrence worked here, Eddington, Ehrenfest. That's a photograph, photo of Ehrenfest, okay? And portraits of Ehrenfest everywhere. None of them, none of the people working there knew that Ehrenfest in 1917, there were three great events. Great October Revolution, De Sitter space was invented in 1917. And in 1917, Paul Ehrenfest explained why our space-time is four-dimensional, okay? And they did not know it. They have shown me his, well, house, etc. They didn't know that this is what he explained. And what he did, he just said that if you solve equations for electromagnetic interaction or for gravitational interaction in d-dimensional space, not space-time, okay, then only in three-dimensional space you have stable atomic systems. And only in three-dimensional space you have stable planetary systems. In four-dimensional they will be unstable, either collapsing or fly away. In two-dimensional, according to general theory of relativity, there is zero attraction between far removed bodies, and the same in one dimension. So we can live only in three dimensions. And then this was considered like a joke. Nobody cared. But if you have this string theory construction, then you have many compactifications which preserve this 10-dimensional structure of space, or some which lead to four-dimensional space. So we have a hint of the explanation why we live in four-dimensional space in general. And then the question, is it just a bad philosophy, or is something better than that? And I have heard many people saying that multiverse theory will never be proven because we will never see these different parts of the multiverse around. And I think that this is silly. And this is silly because people are using method of thinking which is partially outdated and partially, well, put on us by statisticians. We do not always do something and then make an invent a theory and then produce a experiment after that, test it again. Sometimes people do it differently. For example, when you have go to court and somebody killed his wife, you do not give him another knife and another wife and see what happens. You just see whether you can come with an alternative explanation. And that is the principle which was, invented by Sherlock Holmes, who said that when you have eliminated the impossible, whatever remains, however improbable, must be the truth. So if you have an explanation of what happens and You have explanation of small cosmological constant. You may have explanations of why aerospace is three-dimensional. You may have an explanation why proton mass and neutron mass are almost exactly equal to each other with great accuracy. You have an explanation why electron coupling constant is so small and why electron mass is so small, because if you start changing anything like that, life as we know it would be impossible. You have an explanation. And this is explanation of experimental fact. If you can come with a better explanation, then it's fine. But if you cannot, this is experimental facts explained by a theory about which people say, oh, it's impossible to prove it. And finally, I will finish with something which will look like a joke. And maybe it is a joke, or maybe not. It's just, well, last 3 transparencies. So I was challenged. I've seen this episode in Bloomberg TV, and there was this person who was recently retired from Bloomberg TV, this intelligent guy. I always forget his name. Do you remember this guy who was recently, because of the, well, harassment of women, and he retired? No? Okay. Anyway, he was really intelligent guy, and he was well, interviewing one prominent woman theoretical physicist, and everything was very smart, and he was obviously very smart, and she was very smart, and everything was cool. And in the end he said, yeah, but Einstein said that the most incomprehensible thing about the universe is that it is comprehensible. And he waited for her to answer. Because how is that? If you come with all of the theories of many dimensions and brains and stuff, and then you cannot even have a slightest idea why you can actually explain and why is all of this works, what you say. And she was confused, and that was the end of the story. And I looked at them and said, oh my God, they still did not know anything about the multiverse. So look at that. And then I start looking. There was another person who asked a similar question, and that was Wigner, mathematician. He said that unreasonable efficiency of mathematics and science is a gift which we neither understand nor deserve. It's such a self-humiliation in the face of God. We just got this prize, and we totally do not deserve it, but just, well, enjoy what we have. Okay. Then I decided to check whether more recent mathematicians had a better idea about that. And this was what Gelfand have written. Okay? So the reason why Einstein was puzzled by efficiency of physics and Wigner was puzzled by efficiency of mathematics is very simple. They thought that what we have is a universe which is everywhere the same, so no choice. And the fact that we have this nice set of laws is just a gift, no explanation, so we're just lucky, okay? And we're undeserved gift of God to physicists and mathematicians, not to biologists, okay? But in inflationary multiverse, this problem kind of disappears. The laws of mathematics and physics are efficient only if they are predictive. And to make reasonable prediction, you need to have memory which can survive. Just imagine that you are living in a Planckian density universe. Quantum fluctuations during Planckian time immediately erase your memory. You open your eyes in the morning, you have no history, okay? You cannot use your history to predict anything, and therefore you cannot win the game of evolution. If you open your eyes in an empty de Sitter space, there is nobody there except Boltzmann brains. So there are some parts of the multiverse where information processing is inefficient. We can live only in those parts of the universe, multiverse, where the laws of mathematics and physics allow existence of physicists and mathematicians. And this is the picture which I used for description of this multiverse, when it produces new and new parts of the universe with different properties. And then if you look at that, there are some parts of the multiverse where physicists can exist. They look around and they say, and why am I existing here? And why the laws of physics? Oh, because physicists are compatible only with the parts of the multiverse where the processing of information, stable processing of information, is possible. Okay? So I think that I went sufficiently far away, and I hope that at least you will have something to think about in the future. Okay, thank you.
Question? Yes.
The quark-gluon plasma equations for fluid have been learned or measured at Brookhaven and at CERN. Are your inflationary field equations equivalent somehow to the quark-gluon plasma equations?
Quark-gluon plasma existed long after inflation. But I know the situation. This was actually, it's a very deep question about that. I remember how long time ago, before even inflation was started, some person came to Lebedev Physical Institute and saying, I know that the universe started in a vacuum-like state. And I told him, you must be wrong. His name was Glynner. Okay? I told him, no, you must be wrong, because we know that there is asymptotic freedom in the early universe, and the early universe has equation of state, pressure is equal to epsilon divided by 3. And what you're saying is that pressure is equal to minus energy. We know that it is not what happens. Okay? I was wrong. Okay? So plasma, quark-gluon plasma existed after inflation.
In your alpha attractor model, you explained the nice features that it has, but you didn't talk about the motivation for the peculiar looking kinetic energy term. You know, having
Oh no, actually I did. If you start with this geometry, which is often appears in supergravity in particular, that is geometry of Planck array disk, and that is actually something which many people studied independently of what we studied. Okay, we kind of discovered it first without names, but then we found that this is special geometry which has very interesting properties. And then this was illustrated by Escher, who of course lived at the time, which well before inflationary theory. He just illustrated the properties of the Planck array disk. So it's an interesting geometry. Interesting, beautiful is not a proof that this is realistic and that's what really happens. So that is why we need to have Planck satellite to check what we're doing.
The last remarks on multiverse seem at variance with the description of Stephen Hawking's last paper.
Okay, yeah. So actually, if you want to look at this paper, I strongly recommend you. Okay, and then you will find out that in the beginning they say we're using this and this conjecture. And in the end, they say, on the basis of that, we conjecture that. And then they formulate, somehow it did not appear in any discussion of this paper in popular press. Also in popular press, it said that this is like the last message from the genius to all of us, and we need to take it very, very seriously. And it was especially because it was submitted to publication on 20th of April, and he passed away on 14th of March. So this was kind of violation of causality, but that's nevertheless, okay. What nobody noticed is that actually the paper was written in June last year, okay, previous year. So for whatever reason, it was not accepted for publication almost for a year, okay? And you may just ask yourself why. But then, of course, at the moment when it was accepted for publication, it was accepted for publication instantly, okay? So on the 20th of April, it was accepted the same day. And when I looked at it, I don't know. Hawking said many absolutely stunningly beautiful things. And at some stage, he also said that when the universe starts collapsing, death will stand up from the grave. And I said, Stephen. And he said, no, that's it. Okay. So it just, well, genius people, sometimes the spectrum of what they produce is absolutely fantastic. And we judge them for the best of what they said. And as for this paper, the judgment still was not done.
Okay, I think given it's 5:45, I think we'll stop there. And again, thanks, Andrei. Somebody's missing a device